All right, this is chapter 2, chemistry. So let's start off with matter. Typically, matter is anything that occupies space or volume, and what has an effect on the matter as far as weight would be gravity. Matter, yes, it can exist in different forms. Like example for water, it could be a solid, it could be a liquid, and then when you heat it up, it could be a gas. Energy, energy is referring to the ability to do work. So there's different types of energy. Kinetic energies, the energy, think of motion. Potential energy, well, that's a has the potential to do work. So that's what they mean by potential energy. Excuse me. So give an example, think of a dam where the water being held back has the potential to be transformed into a different type of energy. So once they get the water moving, it's kinetic, and then somewhere along they can change that up into electrical. That's a different conversion there to different energy. Again, the types of energy could be chemical. Think of the bonds that hold your molecules like a food together, bonds and gases. That's chemical energy. Electrical energy is movement of charged particles to attraction where there's opposite charges. Mechanical, again, mechanical means the ability to do work. So think of movement. Radiant, electric, magnetic energy, they travel in waves. You could think of like heat, X-rays, UV rays, light as well, travels in waves. Most often, not always, I imagine, but you can convert one form of energy to another, but you can't totally capture it all and convert it to the next. You lose most often, some of that energy in the form of heat when you're converting one type into another. Now, all matter says is composed of elements. Basically, if you think of chemistry, there's a periodic table where you're going to see these letters representing the different elements. The most abundant elements in the body, they're going to be like carbon, hydrogen, oxygen, nitrogen, and there's others, but those are the most abundant in our body. Now, these elements are made up of atoms. Think of the protons, neutrons, electrons, which we'll discuss shortly. Again, most of the elements are represented by letter, like O for oxygen, C for carbon. Some of these elements are derived from Latin, so they're not always going to be represented by the letter that they're spelled out with. So an example, sodium is Na, potassium is K plus. So there's a table in your electronic text. And by the way, please, for whatever reason, these links that I put up to these videos and your book, I'll have to look into. Sometimes they go down. But use the e-text link and it'll take you directly to the book instead of me having to link up a web address to each chapter. It's going to be a lot easier. But anyway, going back to this table, it's in your electronic book version or hard copy. You see some of the elements, obviously the most abundant in the body are elements like oxygen, carbon, hydrogen, nitrogen. And then it tells you some of the uses for these elements. Some other elements you find not as abundant as the previous ones, but like calcium, phosphorus, potassium, so forth. And again, in your own leisure, your own time, you could see what they do as far as functions. And trace elements are these elements you find in the very least amounts in the body. Most often they're needed for optimum activation of enzymes to do their job. Enzymes are proteins that are basically there to speed up chemical reactions in the body. So going to elements, what do they have within them? They have these, it says atoms, which in the middle of the element is a nucleus containing protons, which have a positive charge. And in the nucleus as well are neutrons, which have a neutral, or we say no charge, actually. Think of N for neutral. And then surrounding the nucleus, kind of circling, or we say orbiting around, are electrons, which have a negative charge. Skip that, skip that. So let's look at the picture. So we're looking at the element helium. What distinguishes one element from the other is the number of protons in the element. So if we look here in the nucleus, you have in red two protons. So any other proton, or I should say any other element, they'll have different number of protons. And the protons in the nucleus is referred to as an element's atomic number. So the atomic number here, helium, is 2. Atomic mass, for us, the atomic mass is protons plus neutrons. So the atomic mass of helium is 2 plus 2 is 4. And then the picture on the right, you can see orbiting around the nucleus are the electrons. And remember, electrons, they have a negative charge. Another example of a different element, well, it would have a different atomic number. So hydrogen has an atomic number of 1, since it only has 1 proton in the nucleus, versus helium has atomic number of 2, because it has 2 protons in the nucleus, versus lithium, a totally different element, has 3 protons in the nucleus. When we refer again to the atomic mass, for us, it's going to be the number of protons plus neutrons. So atomic mass, hydrogen still 1 because there's no neutrons. Helium is 4. Lithium is 7. Isotopes, atomic weight, I'll discuss that when the slides come up for those terms. So let's look at these 3 different elements. They're each going to have different number of protons in the nucleus, which is the atomic number. So for hydrogen, you have an atomic number of 1. Helium looks like you have 2. And lithium, there should be 1, 2, 3. So the atomic number of lithium is 3. Now let's look at the atomic mass, which is the protons plus neutrons. Neutrons here in yellow have no charge. Well, for hydrogen, there is no neutron. So the atomic number would be 1. For helium, there's 2 protons, 2 neutrons. So the atomic mass is 4. Lithium, let's see, you got 3 protons, you got 1, 2, 3, 4 neutrons. So the atomic mass here is 7. Okay. Now you're going to notice the electrons in the first shell or orbit, it can hold up to 2. And the outermost electrons in the shell are referred to as valence electrons. So again, atomic numbers, number of protons in the nucleus of an element. It looks like they wrote that lowercase to the bottom left to represent the atomic number. And then atomic mass is the number of protons plus neutrons. And it looks like they write that to the top left of the, with upper script here for lithium. So if I go to lithium, remember it's 7, 3 plus 4 is 7 for the atomic mass. So the atomic mass looks like the right to the top left versus the atomic number is the bottom lower left. Okay, what's an isotope? Well, the best way to look at it is look at the picture. So if you look at these 3 elements, they each have the same atomic number. So technically, it's not a different element. They're kind of like related, like siblings. So an isotope is when an element has the same atomic number, which is the number of protons in the nucleus, but different atomic mass, which is the number of protons plus neutrons. So technically, these are related. They're referred to as isotopes. Now, when you take the atomic weight, not the mass, but the weight, you have to take in consideration of its isotopes. So when you take the weight, atomic weight of an element, it's the average of the 3, the element and its isotopes. So an isotope, again, has same atomic number. So they're related to each other, but they differ in the number of neutrons, which means they have a different mass. And if you're going to take the weight of an element, you have to take in consideration the isotope's weight as well. Now, radioisotope is a type of isotope where it's giving off radiation because it's unstable. So as it's giving off radiation, it's trying to come down to more stable form. Now, elements, when they interact with each other, they form either molecules or compounds. Typically, a molecule, you'll have 2 elements interacting with what's called covalent bonds, okay, versus a compound. They're interacting, but you got two different elements interacting. So let's look at their example. They give us C6H12O6. Well, you have three different elements interacting to make this glucose molecule. And so therefore, this one happens to fit the description of both the molecule and a compound, where you got two more elements interacting through covalent bonds. So it's a molecule, but the elements interacting are also different. So it's also fits the description of a compound. So I would call that a molecular compound. But if you look at here, the examples on the bottom, hydrogen, H2, well, there's two elements, but they're the same. So this one only fits the description of a molecule. Versus as well, oxygen, there's two elements interacting, oxygen, but they're the same. So it's referred to as a molecule, not a compound. All right, now they're going to change gears on us. I would have put this a little bit different, but bear with me. A solution. Let me tell you the definition of a solution. A solution has a solvent which is found in excess amount doing the dissolving. Anything within the solvent found in less amount being dissolved is called a solute. Most often, our solutions that we use, as well as what you find in the body, the solvent is water. Not always the case, but for us, we're going to take the solutions as the solvent being water. Okay. So again, a solvent found in excess doing the dissolving. Solutes are found in less amount being dissolved together to make what's called a solution. So let's take, let me see, your blood. What's the major solvent? Well, water. Anything else dissolved in blood, hormones, electrolytes, minerals, nutrients, those are all going to be considered solutes. Okay, let me skip that. Now, well, let me go back. Some solutions may be in gas form. All right. Most solutions in the body are true solutions. It says a gas is liquid, solids dissolved in. Again, what's the major solvent? We're going to use water. I don't focus so much on this, but when something becomes more concentrated, which means it has more solutes and less solvent, in other words, more solute, less water, that would indicate for us maybe when you're becoming dehydrated. But just to give you an example of a concentration, how is it represented? And this way they can measure how many parts of a solid there are in 100 total parts of solution. Example, 10 parts of salt to 90 parts of water is a 10% salt solution. Whereas milligrams per deciliter, deciliter is equal to 1/100th of a liter. So here there is representing the amount of sugar per deciliter. So normal amounts of glucose levels are around 80 milligrams per deciliter. Molarity, the way I try to rationalize this is think of like it represents a certain amount of something, similar to like a dozen. Dozen of anything represents 12, right? So molarity is a certain amount of molecules, and when you add it to 1 liter of solution, it's called 1 molar solution. So when you have this number, Avogadro's number means a particular amount. This is the amount, 6.02 times 10 to the 23rd molecules. So that's an Avogadro, any substance, just like you would use interchangeably like a dozen. Dozen represents 12. Avogadro number represents this huge number, 6.02 times 10 to the 23rd molecules. If you add any substance, those amount of molecules to 1 liter of solution, you made a 1 molar solution of that substance. All right, solutions. Solutions can be homogeneous or heterogeneous. So heterogeneous, that prefix means different. Think of a solution where if I took samples in different areas of the solution, I don't have the same amount of solute to solvent ratio. Let me see. So let's say I'm going to draw a beaker, which is a container. Bear with me, I'm using a mouse. And there's water in here. That's our solvent. And there's solutes, the ones being dissolved in the water. So heterogeneous means if I took a sample from one area of the solution versus another, I'm not going to see equal amounts of solvent, water, to solutes. Solvent to solute ratio is different when you take in different samples of the solution. That's called a heterogeneous solution. Hetero, again, referring to different. Now, there's two types of heterogeneous solutions. One type is a colloid. So colloid, again, the criteria is I take samples from different areas. I don't have the same amount of solvent. Oops, I was trying to spell solvent. Solvent to solute ratio. Now, if I left standing on its own for a colloid, the solutes do not settle. So left standing on its own, solutes do not settle. And most heterogeneous solutions you can't see through. So that means most heterogeneous solutions will absorb light. Again, I'm using a mouse. Bear with me. So the example in the book they give us of a colloid would be jello. If I give you an example in the body, inside your cells, the water component is called cytosol. So that cytosol is a gel-like solution, would be an example of a colloid. Let me clear these drawings so we can go to our next slide. Now, suspension. Okay, a suspension is also a heterogeneous solution in that, again, if I took samples from different areas, took a sample from one area and the other area, I do not, again, have the same amount of solvent per solute. Again, most light's going to be absorbed, so that way you can't see through it. But with a suspension, if I left it standing on its own, eventually the solutes, due to gravity, would settle. So in this case, this type of heterogeneous solution, the solutes settle. And again, I don't want to spell that out, heterogeneous. So here, solutes do settle to the bottom if left standing over time. Again, let me clear these drawings. Let me step back. Okay, let's go back. Two types of heterogeneous solutions. One's a colloid. The other is called a suspension. Both the colloid and suspension, if I took samples from different areas, the solute to solvent ratio is different. Both absorb most light, so normally, typically, you don't see through it. But the difference between a colloid and solution, if left over time, the solutes do not settle for a colloid versus the suspension, left over time, solutes do settle. So let me give you an example of suspension. Well, here they're giving us an example of sand and water. So if you mixed it up, it mixes thoroughly. Then you set it down on the table. Eventually, you'll see the sand settle. So that's a suspension. The example the book gives you in the body would be blood. Over time, blood, you'd see the heavier components settle to the bottom. Typically, if you have blood drawn out and left to the environment, probably would dry out first. But theoretically, the heavier components of blood would settle. Therefore, fits the description of a suspension. All right, let's look at the three types of solutions here. The ones that we first looked at were heterogeneous. So one is a colloid, one's a suspension. Why are they heterogeneous? Well, if I took samples from different areas of the solution, you do not see equal solute to solvent ratio. That's what the hetero means, different. Now, what's the difference between the colloid suspension? Well, one, the colloid left over time, solutes do not settle, versus the suspension left over time, solutes will settle. And again, for light, most light's absorbed by both the colloid and the suspension. Now, the other solution we didn't quite mention is a homogeneous solution. Homogeneous, that prefix homo means same. So if I took samples from different areas of the beaker here, the solute to solvent amount is the same. So let's think of an example. If this were Kool-Aid, Took an example here versus here, it's still Kool-Aid. I have the same amount of solute to solvent ratio. That's what makes it homogeneous. Over time, solutes do not settle for homogeneous solutions, any of them. And most light's going to be allowed through. Not all light, but most light. So you could probably look through this beaker of water and make out what's on the other side. So those are the three types of solutions. Two of them are heterogeneous. The one on the far left is homogeneous. All right, let's go back to our elements. Elements can interact with each other, and when they do, they'll form specific type of bonds. How do we know when they want to interact? Well, you look at the electrons in their outermost shell called valence electrons. If they're missing any electrons, they will want to interact with another element. If the outermost shell is filled with electrons, they're happy. They will not want to interact. Okay, instead of me reading this, it's easier for me to look at the picture, okay? So you have two elements here. One's helium, one's neon. In the first orbital shell, the criteria is it can hold up to 2 electrons. So helium's happy that that shell is filled. After the first the first shell that can hold 2 electrons, the second one can hold up to 8. And then for us in class, that's it. We're only going to stop there. We're going to go with what's called the octet rule, that second orbital shell can hold up to 8 electrons. Now, if that shell is filled with 8 electrons, it's happy. It will not want to interact. So elements that their outermost shells are filled with electrons are chemically inert elements. They don't necessarily want to interact with other elements. So, just to review that these slides I skipped, the outermost shells of the element are referred to as valence electrons. The atoms after the first orbital shell can hold up to 8. Now let's look at these elements here. Each one's missing a certain amount of electrons in its outermost shell. So hydrogen can hold up to 1 more to complete that first shell with 2. Carbon has 4 valence electrons, would like 4 more to complete its outermost shell. Sodium has what? 1. I'm not going to draw out 7, but it would like 7 in its outermost shell. Oxygen has 6 electrons in its outermost shell, would like to have 2. So when elements are missing electrons in their outermost shell, it's going to tell us they're going to interact with another element. There's 2 ways they can do that. One is they can share electrons to complete each other's outermost shell. And when they share electrons, neither one takes the electron off the other. The other way elements can interact is if you have an element that's very strong and the other one's very weak, one element can just simply strip the electron off the other. All right, so how do we know which elements are stronger than the others? Okay. Well, the way I do it, let's look at hydrogen. It has 1 electron in its outermost shell, but can hold up to 2. So that's its strength. I think of it as being a half pull. Carbon has 4 electrons in its outermost shell, but can hold up to 8. And if you reduce 4 eighths, that will reduce down to a half. So it looks like carbon, hydrogen are equal in strength. Oxygen has 6 electrons, can hold up to 8. So that reduces down to a 3/4. That's its strength. And then sodium has 1 electron in its outermost shell, can hold up to 8. So the strongest one here would be the oxygen, whereas carbon, hydrogen are equal with a half pull. And then the weakest is here, sodium. All right, let me clear that out. Let me get to the next slide. Okay, so what's going on with the electrons if elements are going to interact? Well, ionic bonds, electrons are transferred or stripped. Remember, electron has a negative charge. So this is a scenario where one element is just simply stripped the electron off the other. Covalent bonds, neither element is stronger than the other, so that means electrons are going to be shared. Hydrogen bonds, well, those are the weakest bonds. This is just the attraction of hydrogen to its another element's opposite charge. So opposite charges should attract. So something with a negative charge, hydrogen be attracted to that. They're always indicated below little dots to indicate you're looking at a hydrogen bond. Clear my drawings. Ugh. All right, let's go and review some terms. What is an ion? An ion is anything with a charge. So specifically, something has a positive charge. It's referred to as a cation. Excuse me. If it has a negative charge, it's referred to as a anion. But regardless, whether you see positive or negative on an element, they call that an ion or an electrolyte. Okay, so let me erase this. And so we can get to the next slide. We already mentioned negative charge, that type of ion you refer to as anion. If you see a positive charge on an element, it's referred to as a cation. And opposite charges, they will attract. If you see something with similar charges, they will repel. All right, so let's take our scenario here, see what's going on. So sodium has one electron in its outermost shell, which can hold up to 8. Chlorine first. Chlorine here has 7 electrons, outermost shell holds up to 8. So it's very strong, whereas sodium is very weak. Now, before chlorine strips any electron off sodium, um, when you look at the number of protons and neutrons in the nucleus, I should say protons, just the number of protons, you compare it to the electrons, they're equal. Okay? So you see no charges right now on the left scenario versus the right scenario because each element has the same number of protons as you do electrons. Now, because chlorine's so strong, it just pulls the electron off of it. And when it gains that extra electron, it now has a negative charge. And because sodium loses the electron, it has an extra proton, which now has an overall positive charge. And the element chlorine that became chloride, we say it's been reduced when it gains the electron versus the sodium when it loses the electron, we say it's been oxidized. I'm not going to spell it all out. So these reactions in general for short term are referred to as redox reactions. They simultaneously happen where one element has been reduced, it gained an electron, the other one loses electron, has been oxidized. Okay. So bonds again, where electrons are transferred, stripped, however you want to word it, they're called ionic bonds. So an example is sodium chloride. So NaCl is the molecular formula for salt, sodium chloride. And you notice you have more than one molecule here. So here, what's holding together the molecules are the attractions of opposite charges. The Na plus is attracted to another molecule's chloride, Cl minus. All right, covalent bonds. Covalent bonds are when elements are actually sharing electrons. If they share how can I say? If they share one electron with the other, that's called a single bond. If they're sharing 2 electrons with another element for a total of 4, it's called a double bond. If each element is sharing 3 electrons with the other for a total of 6, that's a triple covalent bond. If they share electrons equally, that is referred to as nonpolar. No one gets a charge. But if they're shared unequally, they refer to that as polar. It's easier to look at the picture so you can understand what they're saying. So let's go back to our carbon. It has 4 electrons in its outermost shell, but can hold up to 8. It has a half pull. If you reduce 4/8, that comes down to a half. Each hydrogen has 1 electron, can hold up to 2 in its first shell. So carbon and hydrogen are equal in strength, but carbon wants 4 electrons, not just 1. So to get 4, what can happen is each of these hydrogens, there's 4 of them, each one can share an electron with carbon. And since carbon has 4 electrons already, can share one with each hydrogen. And now everyone's happy. Each hydrogen has 2 electrons in its outermost shell. Carbon has 8. Now they're sharing electrons equally, which means they were equal in strength. The electrons in the middle of the two. It didn't go more toward carbon or hydrogen. Think of two opponents, opponent A and opponent B, and they're doing a tug of war where the flag is right in between them. Now, if there's a flag in between opponent A and opponent B, if they're equal in strength, the flag remains in the middle, just like the electron did here. So no one gets a charge. So this type of bond, because the electron's in the middle, there's no charge, is referred to as a non-polar covalent bond. Covalent meaning that electrons were shared. Non-polar means the electrons are in the middle. Didn't go neither toward more so the hydrogen, neither did it go closer toward the carbon. The electrons are in the middle. Okay, another thing you want to take note here is this is molecular formula for this type of gas called methane gas. Just like, let's say if I want to write down one molecule of water, you probably already know it as what? H2O. Whereas they drew the methane gas here, you see these dotted or these lines, that's called structural formula. So let's say I want to draw the structural formula for water. I'll draw 1 oxygen and then 2 hydrogens. And I drew one line indicating that each element, hydrogen is sharing 1 electron with oxygen, and oxygen sharing 1 electron with both of each of these hydrogens. It's called structural formula. And this is called a single covalent bond when each one's sharing 1 electron with the other. Had you seen 2 lines, then they're sharing 2 electrons with the other. All right, let's clear the drawings. Let's move on to the next scenario. Okay, so this scenario, you have 2 oxygen molecules. Each has 6 electrons, can hold up to 8 in its outermost shell. That reduces down to a 3/4 pull. They're equal in strength. They both need, what, 2 electrons to complete their outermost shell. So what they'll do is each one will share 2 electrons with the other. And because they're equal in strength, it's in the middle. I don't see any charges. So this again is a nonpolar. And then because electrons are being shared, you say covalent. Nonpolar covalent bond. And because they're sharing 2 electrons with the other, you can also refer to it more specifically as double bond, nonpolar double bond covalent, because this here is indicating a double bond. And let me bring to your attention, each time they share more electrons with the other element, the closer they get to each other. So let's just give a scenario. Reactant or element A is sharing an electron with element B. Okay? They're just sharing one with the other. Now they share 2, each one sharing 2 with the other, the closer they get. So if they share more than 1 electron with the other, they're going to get closer, and those bonds are stronger. So a double covalent bond is a lot stronger than a single covalent bond. I like thinking of a stick, excuse me, So if you got a long stick, it's going to be easier to break than a short stick, right? So indicating here more than one electron being shared with the other, it gets shorter, the distance between the elements, making the bond stronger. All right, let's go to the next slide. And what we have here is a gas, or not a gas yet, nitrogen. So when you have two nitrogens, each one lacking 3 electrons in their outermost shell, each one can share 3 with the other, and they're equal in strength. So they're right down the middle. And because you're sharing 3 electrons with each other, they get so close to each other. These are the strongest type bonds, a triple covalent bond. They're harder to separate. And now you form one gas of nitrogen. N2. Okay, those were examples of nonpolar covalent bonds. We're looking at carbon dioxide, which is a gas. And looking at the structural formula, I could tell because they draw 2 lines here. Each element, oxygen and carbon, is sharing 2 electrons with the other. So everybody's happy. And there's no charges here because on the other side of the carbon's oxygen to counterbalance it. So normally, oxygen is stronger than carbon and would normally pull the electrons closer toward it. But since there's another oxygen here on the opposite side, keeps the electrons in the middle. So this again would be an example of nonpolar, and these will be double covalent bonds. All right, could we see a scenario where we have one element pulling the electrons a little bit closer, but yet still sharing? So let's look at what's called a polar covalent bond. Okay. Let me just make sure we are recording. I believe we are. So an example of polar covalent bond. So here you got water. So again, oxygen is stronger than hydrogen. So it's just pulling the electron, didn't pull it off, but it's pulling it a little closer toward it. And yet the electrons are still being shared. So the electrons are shared, it's still a covalent bond. But in this scenario, because the electron is closer to oxygen, you're going to see some charges. You're going to get a partial negative charge on oxygen because the electron is closer to it. And then you get a partial positive charge on the hydrogen because it's losing, not totally losing, but sharing its electron a little bit further away from it. So this is a polar covalent bond. And clear the drawings. So to review the bonds, if you have a covalent bond, you typically want to remember for covalent bonds, no matter what, electrons are being shared. If they're shared equally right between the 2 elements, no one gains a charge. It is non-polar. No charge, non-polar. Now, polar covalent bonds, covalent again, electrons are being shared, but however, the element, one of them is pulling the electron a little bit closer toward it. So that's when you start seeing charges. So when we see charges, it is polar, yet it's still covalent because the electrons are being shared here. The example was water. And then the weakest bonds are gonna be the ionic bonds, and not the weakest, the second weakest. So what's going on here is that the chloride totally stripped the electron off sodium, and when it strips the electron off sodium, we say it's been reduced, whereas the sodium's been oxidized. So when electrons are stripped, transferred, however you want to visualize it, you form an ionic bond. And what keeps it together is the attraction of opposite charges. Positive and negative will attract to each other. Clear my drawings, go to the next slide. Hydrogen bonds are the weakest, okay? Let me just get to the picture. It's going to be easier to see. So when I'm looking here at a hydrogen bond is the attraction of hydrogen to another molecule's opposite charge. So look at the charge on hydrogen here. Even though it's partial, it is positive. So opposite charges attract. So this hydrogen's partial positive charge is attracted to the oxygen's partial negative charge. And hydrogen bonds are always indicated by dash little dots in between the elements. And these are the weakest type bonds. So if you ever think of water, yes, water is easy to separate when it's in liquid form. It also takes the shape of a container. So weakest bonds are hydrogen bonds. Now, surface tension. What is surface tension? Well, surface tension is the attraction of water to itself through the hydrogen bonds and to any surface it touches, in this case, the bug here. It looks like it's on water, like walking on water. Why? Because of surface tension. So let me give you an example of surface tension. Have you ever been rained on with your clothes on and you're drenched and the clothes are sticking to your skin? It's because of the attraction of water to itself, to your shirt, and to your skin. And that creates surface tension. Another example of surface tension, you may have little trouble separating pages of a book, but if you apply a little moisture to your finger, you'll create surface tension where it'll stick to the page and you can turn it. So that's an example of surface tension. All right. Chemical reactions. Any reaction that takes or happens in the body goes under the term metabolism. Typically, what you start off with in a reaction are called reactants, and what you end up with are called products. So let's give an example. I'll draw two variables, reactant A and reactant B. So let's say I'm putting them together and I formed a product. Okay. So you'll notice I had single units and I put them together, I made something larger. So this is called a synthesis reaction. You made something. Okay, this is going to take me forever, so I'll just leave it at that. Now, typically when you put things together, water comes out of the reactants. Where did the water come from? Well, it comes from the reactants. H plus OH is H2O. So this synthesis reaction, since water came out, can more specifically be referred to as a dehydration synthesis reaction. Dehydration, meaning water came out during the reaction. All right, now, what if, and let me just tell you, in the body, reactions are most often reversible, which means they can also go in the opposite direction. So to give you an example, if you're getting nutrients and all, you'd be building up, but if you're fasting, then you're going to be breaking down those nutrients. So let's go the other way now. Let's say you have reactant AB, because we're starting here, and then we broke it apart and we formed products A and B. It's just the opposite of the reaction I drew in red. But since we start off on this side, going to the left, AB is the reactant, whereas when you separate them, they're products. And to separate them, water needs to come in to separate into products. So this type of reaction in blue, when you're breaking something down, it's often referred to as a catabolic reaction, or we say hydrolysis reaction. You add water to the reaction, H2O, so you can break it down to smaller units. Hydro referring to water, lysis referring to breaking. Right? Don't take me for sure on that I, could be E. We'll find out in the slides coming up. All right, let me clear these out so we can go to the next slide. All right, so here, let's see, we got some molecular compounds, water, and you also have sugar here. These are held by covalent bonds. So let's say here going from left to right, you have the reactants, you got hydrogen, well, H plus H, hydrogen make hydrogen gas, H2. Going from left to right, the one left is reactants, and what you end up with are products. CH4, what you start off with again, 4 hydrogens, 1 carbon. Those are the reactants. What you end up is with product, methane gas. So when you're building something from small to large, that's a type of synthesis reaction, or you can refer to as anabolic. I like to think of anabolic steroids to think you're building up. So A plus B here on the left are reactants, and you built something, you made something larger, it would be the product. That type of reaction is known as dehydration synthesis reaction. You could also refer to it as anabolic reaction as well. So here you're looking at amino acids. Amino acids are what you need to put together to make what's called a protein. So the reactants here in this case are amino acids, and the product would be a protein. So this would be a synthesis reaction, or anabolic means building up. Breaking something down, catabolic reactions, also known as decompositions reactions. So here you got the reactant AB, and you want to break it apart into products A and B. Um, Actually, you need to add water to separate those. But going back here, it's known as decomposition, catabolic, or you say hydrolysis reaction, since you need to add water to separate. So an example here, the storage form of glucose is called glycogen. And if I want to break it apart into smaller units, that would be glucose. So catabolic, or you say hydrolysis, you're breaking glycogen down into glucose. Exchange reactions can also occur in the body where you're swapping out portions with the reactants involved in the reaction. So to look at the example to give us here, you got AB plus C. These would be reactants. Notice AB is going to give up a portion to add to well, the B comes off, and therefore the C is added to the A. So you're swapping components involved in the reaction. Same thing here, they're swapping components involved in the reaction. So those are called exchange reactions. An example of an exchange reaction of the body, well, ATP. ATP stands for adenosine triphosphate. Triphosphate, tri means three phosphates. This is the molecule all cells need to produce in order to survive and do work. And what you got here are three phosphates with similar charges. Things that have similar charges don't like being next to each other. But if you could force it next to each other and hook them up, that way when you break this bond, they're going to repel from each other, and that provides energy to do work. So they give us this molecule ATP, which stands for adenosine triphosphate, that when it gives up its phosphate to do work, is an example of a exchange reaction. And just to kind of describe ATP a little bit more detail, you have the nitrogen-based adenine, which in its structure has nitrogen. You have the sugar here, ribose, and then you got three phosphates indicating triphosphate. Let me clear out the drawings. Go to the next slide. Okay, what do we have here? Atoms are reducible. Okay, there's those terms I brought to your attention earlier. Anytime you have an element gaining an electron, the term is that we say it's been reduced, whereas if an element loses the electron, we say it's been oxidized. Okay, you can't typically see here where the electron's moving, but that's the definition of these terms. Again, let me clear the drawings out. All right, let me go back to our reactions. Now, let's see, I have reactant A plus reactant B, and you put them together to make something larger. So that's known as anabolic reaction. Well, we need to focus on that it's called a dehydration synthesis reaction. You made something. And typically, when you form something like this, you put something together, heat's going to be absorbed from your environment. So anytime heat is absorbed from your environment during a reaction, you refer to it as endergonic. All right, let's do the opposite scenario. Let's say I have the product, or let's say in this case, it's now reactant AB, and I want to break it down into products, single units A and B. So breaking something like this down, we want to focus I know it's catabolic, but I want to focus on it as a hydrolysis reaction. I need to add water so that it separates. And when you have catabolic reactions, also known as hydrolysis reactions, you lose some energy in the form of heat. So as heat is being released, those reactions are referred to as exergonic. And notice I said this bottom was an example of catabolic, which is also known as a hydrolysis reaction. All reactions are theoretically reversible. Okay, example, when you're eating, you're taking nutrients and you're building up. So let's say A and B are the nutrients and you made something larger. You took amino acids from your diet and you made proteins. Vice versa, if I drew the arrow the other way, it means I could, when I'm fasting, I can also take that protein or nutrient and break it down to use for energy. So anytime you see double arrows going either direction, that means the reaction is reversible. What can increase the speed of a reaction? All right, let's get back to my marker. So let's say I have reactant A and I have reactant B. So if I apply heat, the quicker reactant A can get to reactant B to form product AB together. So temperature, if there's heat, will make a reaction go faster. But if you lower temperature where it's cold, the reaction will go slower. All right, concentration is referring to the amount, and the more reactants you have, there's less space between A and B, the quicker they can meet to form product. So the higher amounts of reactants, you'll form product faster. Size of the reactants. The smaller the size of the reactants, the quicker they can move toward each other, again, to form product. And last but not least, the presence of a enzyme. What are enzymes? Enzymes are proteins that speed up chemical reactions. So enzymes, when present, can make a reaction go faster. Just take note, not all proteins are enzymes. Let's say your muscles, protein, but that's not an enzyme. Okay, next slide. So another name for enzymes, they refer to them as catalysts. Basically, it's an enzyme to speed up a chemical reaction. All right, now let me get to the second PowerPoint. Okay, make sure we're recording. Yes. So this is the second PowerPoint, chapter 2. How do we know when something's organic? Typically, something organic has to have carbon within its structure, with the exception of it not being a gas. So anything with carbon, as long as it's not a gas, we'll consider organic. So sugars, fats, proteins, they have carbon in their structure or organic. Whereas water, salts, things like that, they don't have carbon within their structure, we'll consider inorganic. What do we got here? Heat, high heat. Oh, they're talking about water. And we're not going to focus so much about how much heat capacity it has and things like that. Okay. But I do need you to know that anything with a charge is polar and will interact with water. Water is polar, which means separation of charges. Okay. So typically, anytime you see a positive or negative charge next to an element or water, it's polar. And the major solvent in our body is water. So here, let's look at the salt. Salt is a compound, but when it hits water, it's going to form electrolytes. In other words, ions. So let me get my marker out again. So the molecular formula for salt is NaCl. And for water, the structural formula, I'll draw it out structural wise, is H2O, right? Now we know water's polar. Oxygen has a partial negative charge. Hydrogen has partial positive charge. So sodium, salt, is going to ionize, in other words, form ions when it hits water. Why did it form ions? Because of the attraction of opposite charges. Sodium is attracted to the oxygen's negative charge, and then chloride has a negative charge. It's attracted to the water's hydrogen's positive charge. So any compounds, when they hit water, they ionize and form electrolytes. What's an electrolyte? Basically anything with a charge. It came from a compound that ionized into electrolytes. Ionize means to separate and form ions. Ions like cations, which is positive, or anions, which are negative. All right, let me clear my drawings. Go to the next slide. So the literal definition of a salt is any compound that ionizes when it hits water, with the exception that it's not an acid or a base. Any compound that separates into electrolytes, with the exception of it not being an acid or a base. And what are acids? Acids are compounds that donate hydrogens when they hit like water, and bases are compounds that ionize and donate hydroxides, OH minus. So all ions, when they hit in water, they're referred to as electrolytes. Okay, anything with a charge, basically. Whereas an acid or a base, the definition of an acid, well, let's give an example like hydrochloric acid, HCl. When it hits water, it's going to ionize into hydrogen and chloride. Okay, so anything that donates hydrogens when it hits water is considered an acid. Now, clear my drawings out. Whereas the base does the opposite, basically. Bases, oftentimes we say they uptake hydrogens, but let's look at the base NaOH, okay? You got sodium hydroxide, and that's a base. It is a compound that when it hits water is going to ionize into electrolytes, Na plus sodium and OH hydroxide. So we said acids donate hydrogens, but bases will uptake them. Why? Well, when a base hits water, you have this hydroxide floating around. And if there's any hydrogens around it, it will add to the hydrogen and make water, H2O. You have one hydrogen here, one hydrogen here, counting for the two. And there's the O, counting for now making H2O. So bases typically uptake hydrogens, whereas your acids, they donate hydrogens. At least that's how I remember it. If you want to say bases, when they hit water, will ionize and donate hydroxide to uptake hydrogen, well, that's just another way to say it. All right, let me clear the drawings before we can move on to the next slide. Now, when you look at the pH of a solution, what do they mean pH? The P stands for percent, how much? How much of what? Well, the H stands for hydrogen, okay? So the pH of a solution, there's a scale. The scale's from the number 0, not 1, but 0 to 14. Excuse me. Within the middle being a pH of 7. So when you have a solution and let's say there's more hydrogens in the solution, and I draw these little boxes to indicate concentration, how much. Doesn't say exactly how much, just means amount. So if you have more hydrogens in a solution where the number is below 7, we say the solution is acidic. Whereas you got more of the OH, the hydroxide, in a solution, anything above 7, we say the solution is basic, or you say it's alkaline. Now, what happens if you have a solution, but you have equal amounts of hydrogen and OH, hydroxide? We say the solution has a pH of 7, and you would call it neutral. All right, now let's say I have a pH of 3. That would be acidic, right? It's below 7. And let's say I have a pH of 4. Well, that one also is acidic. Okay. Now, the lower you go in the number, the amount of hydrogens would increase. So anytime you go between numbers, the lower number is going to have more hydrogens. And between each number, you have 10 times more or less hydrogen. So to give you an example, excuse me, the pH of 3 has 10 times more hydrogen than a pH of 4. Or you can reword this where you say the pH of 4 has 10 times less hydrogens than the one at 3. So anytime you see numbers for the amount of hydrogens, we do it in multiples of 10 for the difference. So give another example. All right, let's do pH of 3, and I'm comparing it to pH of 5. Both are acidic, okay? Again, the pH of 3 has more hydrogen. How much more? Well, let's draw the steps in between 3 and 5. There's a 4, right? So between 4 and 5, the pH of 4 has 10 times more hydrogen. And between 3 and 4, pH of 3 has 10 times more hydrogen. So when you compare pH of 3 versus 5, you have to do 10 times 10. 10 times 10 is 100. So pH of 3 would have 100 more hydrogens in comparison to 5. Again, we do it in multiples of 10. All right, clear the drawings out. Let's go to the next here. Okay. Oh, I got to go back to the marker again. Believe me, that's no fun when you're using a mouse. All right, so remember it's a scale from 0 to 14 with the midline being 7, right? So anything between 0 and 6.99999, not 7, but right below 7, the solution is acidic. If you have equal amounts of hydrogen and equal amounts of the hydroxide, your pH is 7, you say the solution is neutral. Trying to draw this out. Okay, that's when you have equal amounts of hydrogen and hydroxide. And when you have a scale anywhere from 7.01, not 7, but 7.01 to 14, we say the solution is basic, or you could say alkaline. So anywhere between 7.01 and 14, not 7, right? 7.01, we say the solution is basic or alkaline. Okay, this is in biochem. Look, don't worry about that. If anything has a pH number, just write in logarithm to the negative exponent. So if it's pH of 7, just write -7. Well, I'm not going to go into specifics and formulas, things like that. All right, let me clear the drawings, get to the next slide. Yeah. So here's our scale. It's a scale from 0 to 14, right? Things that are acidic, you should know have more hydrogen. So like lemon juice has a pH of 2, wine pH of 2 between 2.5 and 3.5. Anything alkaline or basic would have a pH above 7. So examples, bleach has a pH of 9. Okay. Anything with equal amounts of hydrogen and hydroxide, we say solution's neutral. Take note that your blood is a little bit alkaline. It's not quite 7, it's a little bit above 7. So pH here is 7.4. We say it's alkaline or you say it's basic. Okay, clear drawings. So what do we got here? Okay, what is a buffer? Buffer is anything that will negate a pH change, whether you're adding an acid or a base. Anything that will resist changes in pH where you're at, whether you add an acid or a base. So an example here could be carbonic acid bicarbonate, which is a weak acid, weak base. Okay, I'm going to do this. I got to go back to the pen here real quick. All right, so H2CO3 is a weak acid, whereas bicarbonate is a weak base, okay? This here I'm drawing out as bicarbonate, it's weak base. Now, if you recollect, acids donate hydrogens, right? So typically, let's say if I added hydrochloric acid, which I'll draw up here, and this is one molecule of hydrochloric acid. Let's say if I have three. So when it hits water, what's going to happen? That's going to ionize into hydrogen, and there's going to be three of them floating around. And if the pH was 7 before you added the acid, and P stands for percent, it's always lowercase, and the H is uppercase for hydrogen. So if I add the acid and this is floating around, that will lower my pH and it'll start to drop. Okay, so buffer would resist changes in pH. So let's say this is floating around after you add the acid. Which one can negate it so it doesn't affect the pH would be bicarbonate. So what would happen is this will hook up here to the bicarbonate and that will make H2CO3. So no longer with that hydrogen be floating around. Oh, look at that. I can erase that. Interesting. All right. So let me go the other scenario and let's add a base, okay? All right. Let me go back to the marker. Gotta find the commands for it. Give me a minute. Huh. It's not gonna let me. Interesting. Let's just clear all drawings in and close that out and have to go the long route. Oh, joy. It's not gonna let me do it. I can undo that. Maybe I can go back a little in. Oh, joy. Yeah, it's not gonna let me go back to the marker for whatever reason. Let me just clear my drawings out. Let me close it. And let me just explain. Try to without drawing. So a base just does the opposite. This buffer, which is the carbonic acid, is going to negate the effects of a base. So if you go with the literal definition of buffers, anything that will resist changes in pH, whether you're adding an acid or a base. Okay, let me just see one more time if I can. No, it's not going to let me do my drawings no more. Joy. That's not good. Oh, well. All right, let's look at our reactions again. Any reaction that occurs in the body goes under the term metabolism, okay? Most reactions, again, theoretically are reversible, which means they can go in either direction depending on the body's needs. So let's take the first scenario up top. You have two single units, you put them together to form something larger. We want to recognize that as a dehydration synthesis reaction, where dehydration is referring to the water came out of the reactants, and synthesis is that you made something larger. Now let's go to the second column here, or I should say row, in the middle. You have one single unit and you want to separate it into smaller units. You need to add water to separate. So letter B is referred to as a hydrolysis reaction. You add water, lysis means to separate or break. So that's breaking down. On the bottom scenario, you've got here some sugar where you have single units and you form something larger to the right. So that's a dehydration synthesis reaction. But because the arrow goes in the opposite direction, it can also go that way. When times where your body needs, it can break it down by adding water. So going from right to left in letter C is known as a hydrolysis reaction. So again, reactions are reversible pretty much in the body. So theoretically, I didn't even have to draw or look at the row B. You could have just in letter A drawn an arrow going both directions to indicate the reaction is reversible. Sorry, I'm taking my time trying to see if I can get my drawing pen back. And oh, let's see. Draw. Here we go. Got it back. So again, instead of drawing that letter B out, I could have just drawn an arrow this way, meaning the reaction is reversible. All right, let me clear my drawings now and we can go to the next slide. All right, we need to know what are the single units that make up large sugars? Well, large sugar is often referred to as a carbohydrate, and carbohydrates typically have carbon, hydrogen, and oxygen in their structure. So when you're breaking down carbohydrates before you can deliver it to cells to make ATP, you need to break it down into the simplest units, and the simplest units are called monosaccharides. Monosaccharides means one simple single unit sugar. Now, if I put two sugars together, right, and they're hooked up, well, then you form a disaccharide. Di means two. If it's more than two, well, then you form polysaccharide. And then you get into hundreds to thousands, then you form your carbohydrate. So if you ever ask what are the single units to make up carbohydrates, the correct answer should be monosaccharides. All right, let's clear my drawings, go to the next slide. I don't want to read all that. This picture's kind of small, but this is a typical your monosaccharides. How do I know I'm looking at a monosaccharide? Well, for one, they're always going to have carbon in their structure. They're always going to have hydrogen in their structure, and they're always going to have oxygen in their structure. And they're held together by covalent bonds. So anytime you look at this and it comes to a point and there's no letter here, it's understood to be a carbon. Okay. So if I were to count up all the carbons and hydrogens and oxygens and reduce them, they always fall in a 1-to-1 ratio. Well, I shouldn't say always, most often, okay? So let me give you an example. Let me clear my drawings again. So let's count the carbons on glucose, all right? So there's nothing here in front of this point. That's one. That's one carbon, two carbons, three, 4, 5, and then up here 6. So far that's 6 carbons. So we always said they were going to fall in a 1-to-1 ratio, right? So I don't even have to count the hydrogens. I know there should be what? 2 times 6 is 12. And then for oxygen should be 6. Now let me count the hydrogens regardless. Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then here's a 2 for the 12th. And don't make me count the oxygens. There should be 6. Okay, so for carbohydrates, they're ring structures held by covalent bonds where they have carbon, hydrogen, and oxygen in their structure. And most often, when you reduce the carbon, hydrogen, oxygens, they're going to fall in a 1-to-1 ratio. Okay, let me close this so I go to my next slide. Disaccharide, well, that's just when you put two monosaccharides together, okay? So here you're looking at a couple of disaccharides, sucrose, maltose, and lactose. And I'm just going to tell you right now, if you see in the spelling OSE, O-E-S-E, those are usually referring to sugars, okay? The other thing I forgot to mention about enzymes, in spelling, they usually end in ACE, lipase, oxidase. If it ends in ACE, it's an enzyme. Polysaccharides, well, that just means you have more than one sugar, more than two actually added together. You form a polysaccharide. So here an example of polysaccharide is our friend here, glycogen, which is a storage form of glucose. So in your diet, when you get glucose, unless you're diabetic, you normally don't get rid of it. You'll hook them up into what's called glycogen, and then you'll store it in the liver as a fuel reserve. And then any extra glucose after that, well, then your body can change it up into a lipid and store it that way. Lipids. The main thing I tell students to get from lipids is that you need to recognize them as non-polar. That means they don't have any charges, which means they will not interact with water, which means they're water-fearing, hydrophobic. But the main thing, again, non-polar. So some examples of lipids can be a triglyceride, phospholipid, steroids, and then eicosanoids. So what's similar between them all? They're nonpolar. So lipids we can use for energy. Depending on the type of lipid, can also be a steroid as well. Okay. Lipids, if it's like fat, well, we can use that for fuel reserve. We can also use it for insulation, protect some of the organs as well if they're located, if the lipid's located surrounding the organ. So this is an example of well, normally there'd be three fatty acids, which is a long carbon chain with hydrogen, but this is a monoglyceride, which means you have one fatty acid chain attached to glycerol. And it's a type of lipid because the fatty acid, you don't see any charges here. Let me see. I don't see any charges on the glycerol either. So it's nonpolar. Now, triglyceride, you still have glycerol component, but now you got three fatty acids attached to the glycerol. So it's a triglyceride. And this is structural formula, how they would draw a triglyceride. Okay. This isn't a chemistry course. I'm not going to make it that difficult. Okay. But heads up, you have something similar like this on your lab quiz for, not lab quiz, your lecture quiz number 2. Okay. Saturated. Well, how do you know when a lipid's saturated versus unsaturated? Okay. Well, the fatty acids. The fatty acids was just a long carbon chain with hydrogens attached, right? So here you got carbons, and I'm not even drawing the whole fatty acid chain. And then here are the hydrogens. What you want to take note is look at the bonds, the lines. Each carbon, each hydrogen sharing one electron with the other. These are single bonds, indicating each element sharing one electron with the other. So anytime you have a lipid and all you see are single bonds, we say it is saturated. Okay. Now imagine the other slide's going to say unsaturated. So let's have a look at that real quick. No, they're showing us saturated. So think of things like our lipid like if they come to room temperature, they'll form a solid like butter or lard. They have single bonds all between the carbons. Now, unsaturated, that's a little, not too much different. It's still a lipid in that you don't see anything polar, you don't see any charges. But now between the carbons, you see double bonds, indicating that each carbon is sharing 2 electrons with the other. So anytime you see double bonds between the carbons, it's unsaturated. If you see more than one of these double bonds, we say it's polyunsaturated. Okay. And typically these will remain in liquid form at room temperature. So think of plant oils, olive oil. You'll see here double bond causes a bend in this fatty acid. It's unsaturated type of fat. All right, now phospholipids. Yes, it's a lipid where a part of it's polar and then the lipid part is non-polar. So things that are polar, they do like mixing with water. So things that are liking mixing with water are hydrophilic, and things that do not like mixing with water are hydrophobic. So when you look at a phospholipid, you're going to see the phosphate part. They usually draw like a circle, and the lipid part, they'll draw like a tail, a head, and a tail. So the phosphate part is polar. So we say it's hydrophilic. And then the tail portions, your lipid, is nonpolar. And things that are nonpolar are hydrophobic. Okay. So why they even bring this up? Well, because our cells, the membrane, think of a cell, nice circular. What makes up the membrane is a bilayer of phospholipids. Inside the cells, water type environment. And then outside the cell is also a water type environment. So when you have phospholipids, the polar part will be facing the water. So your cell membranes is a bilayer. Bi means how many layers? 2. So one layer, it's oriented where the phosphates face the water environment outside the cell, H2O. And then the other layer, because we said it was bilayer, faces the water environment inside the cell. See, the phosphate here is facing the water environment inside the cell. So that means the tails, they don't like water. They don't have to be exposed to water because it's facing the other layer, which is oriented in the opposite direction. Okay. So again, phospholipids is a unique type lipid where the phosphate is polar and the tails, the fatty acids, are nonpolar. Let me clear the drawings. So here's our picture of our phospholipid. Again, the phosphate in purple is representing the polar part, likes mixing with things like water or things that are polar as well. Where in the yellow part is a fatty acid. Don't like water. It's not going to be facing water. It's nonpolar. And again, anything polar likes mixing in water. The term is hydrophilic. And things that are nonpolar don't like mixing in water or water-fearing. They're hydrophobic. So again, with my generic drawing, I was trying to draw bilayer phospholipids, where that represents what makes up the major structure of our cell membranes, a bilayer of phospholipids, with the phosphate being polar, which is known as hydrophilic, and again, the tails nonpolar, hydrophobic. All right, another type of lipid are steroids, and steroids are derived from cholesterol. Cholesterol is a ring structure type lipid, but the key thing is I don't see any charges, so it's a lipid. It's a ring structure. It's called cholesterol. So a lot of steroids are derived from cholesterol. Anyway, I don't want to read all that. All right, proteins. Let's move on. What are the single units that make up proteins? They're called amino acids. Okay. And amino acids, when they're held together between each other, they're held together by what's called peptide bonds. Now, what are some of the elements you see in a protein? Sure, you're going to see carbon, you're going to see oxygen, hydrogen, nitrogen, and phosphate. Oh, the S stands for what? Sulfur. Just take note, not not all proteins are enzymes, but enzymes are proteins that will speed up chemical reactions. So, an example of a protein that's not an enzyme, think of your muscles. So, some examples here, you may see some proteins, excuse me, making up the structure, to hold components inside the cell. You may see a protein actually being an enzyme, or proteins like in this case hemoglobin, which you find in red blood cells to carry oxygen. Some proteins are needed for muscles to contract, so some portions, yeah, a good amount, all of the portions of the muscle are pretty much proteins. You may see proteins embedded in the cell membrane having a function where it may be a channel or a generic term called a receptor, where something binds to it and then it does something. You may see some proteins made by white blood cells that are called antibodies that are there to keep you from getting sick from things like viruses. All right, again, I don't want to have to read all this. Let's just look at the amino acid. The amino acid are the monomers that make up proteins. There are 20 different amino acids. There should be a table somewhere in your electronic version of the textbook toward the end that will list all the different amino acids. Okay? So in an amino acid, you're always going to have this component here. I learned it as the carboxyl group. You have C double bond O, and then you have single bond to OH. That's called the acid group. Again, I learned it as carboxyl group. You'll always find that in an amino acid. And then you'll also have NH2. This is called the amine group, and ends the nitrogen, okay? You'll always see these in amino acids. But what makes an amino acid different from the other is what's located, represented by R. R is a variable. Just like in math, a variable can mean any number. Well, R in this case is called a functional group, which could represent anything element-wise being there. So if you have a hydrogen here, well, that's one type of amino acid. If something else were here besides hydrogen, would be a different amino acid. But consistent between every amino acid is this bottom portion, okay? The amine group and the acid group. And how many different amino acids types are there? There's 20 different amino acid types. Okay. So here you got a couple amino acids, you put them together, you form a dipeptide. What's holding these together is called a peptide bond. Water came out when you put the amino acids together. So going from left to right, you need to know it as a dehydration synthesis reaction. Now, if I break it apart by adding water and separating it out into simple units, we need to know that as a hydrolysis reaction. And the double arrows means the reaction can go either way, any direction, depending on your body's needs. Okay, the levels of proteins. All right. Well, when you put the amino acids together to form proteins, let me see if I can get my marker back. So I'm just draw little round circular structures representing the amino acids, and I'm hooking them up by peptide bonds. So when I put them together, similar to like a rosary with beads, this is called primary structure. Primary. All right, the next structure of a protein may be in secondary structure. So secondary structure, you still have this scenario with beads, right? What I drew in primary. But now, not only could it take a helical format, but what you see in between the amino acids are hydrogen bonds. Hydrogen bonds are always indicated by little dot lines. And remember, hydrogen bonds are the weakest bonds. So it can be an alpha helix, which means it took on a like a ribbon format, helical format. Well, that's the way I know it. But if you could think of a ribbon twisting, that's alpha helix. Or it could be a beta pleated sheet. Think of an accordion or a roller coaster going up, down, up, down, up, down. But how do I know it's in secondary structure? Are the amino acids are held together pretty much just by hydrogen bonds. And remember, hydrogen bonds are the weakest. All right, after secondary structure, you may and will have what's called tertiary structure. Okay, how do I know it's tertiary structure? Is when you see the amino acids held by covalent bonds. So covalent bonds means the electrons are being shared, and covalent bonds are stronger than hydrogen bonds. In order to break these bonds, you would need heat. Okay, so think of folding up that rosary with beads, like crunching up paper. It's in a three-dimensional format, and what's holding its structure together now are covalent bonds, which means electrons are being shared between the amino acids. And in order to break these bonds, you would need heat. All right, quaternary structures, the next level. Now, quarter technically is referring to four, but in our scenario, the definition for quaternary is all we need is two or more separate proteins interacting to make one molecule. So there's protein number one, there's number two. They held together by magic covalent bonds, and you made one molecule. Can you have up to four? Yes. But all you need is two or more making up one molecule. You're in what's called quaternary structure. All right, I'm not going to read all that just for time's sake. You can read that on your own. I focus on what we need to get out of the chapter, okay? Now, remember quaternary, tertiary structures held by covalent bonds, right? Well, what would happen if we applied too much heat to our enzyme? Well, let me draw up my enzyme, okay? I did, it was in, this one's tertiary structure, right? It's all in three-dimensional format, and it's held together by covalent bonds. So when you apply too much heat, a little heat will make the enzyme go faster, but too much heat will break your covalent bonds here, and your enzyme will unravel, and it no longer works. When the enzyme's been unraveled, it no longer works because you applied too much heat. We say the enzyme has been denatured. You can't get it back. Well, how about if I decrease temperature? Well, if I decrease temperature, that doesn't necessarily break the bonds. It just slows the enzyme down. Okay. Now, the scenario I was given as a student is think of an egg. If you apply heat and you scramble the egg, it's basically like denaturing your enzyme. You can't get back what you originally had. Okay. So let's just review. When you decrease temperature, it's cold, the enzyme slows down. But if you increase temperature a little bit, it'll go fast. If you increase the temperature too much, too hot, that'll denature your enzyme. And again, what are enzymes? Well, they're proteins, and they're there to speed up any chemical reaction, whether you're building up, breaking something down, or swapping components involved in a reaction. But are all proteins, I should say, are all proteins enzymes? No. Think of your skeletal muscle. It's protein, but it's not an enzyme. Enzymes sometimes need minerals or vitamins called cofactors and coenzymes so that they can fit to what it attaches to perfect and they make the reaction go faster. All right, what am I talking about? Well, let's go back to the drawings, okay? So I'm going to draw my enzyme like Pac-Man this time, okay? It doesn't look like Pac-Man. And whatever the enzyme binds to is referred to as the enzyme substrate. Well, sometimes it doesn't quite fit the substrate until a vitamin or minerals present. Once the vitamin or minerals present, it'll bind to it somewhere other than the active site. The active site's where the substrate binds. So once the mineral's present or the vitamin, then it takes the right shape, let's say to fit to the substrate, and it works good. Okay, so some enzymes, they need the presence first of what you have a mineral or vitamin called a cofactor before it can fit the shape of the substrate, so it works faster. But I'm just going to tell you now, all you need to know is what enzymes are. They're proteins that'll speed up chemical reactions. Okay. Cofactors, coenzymes. Okay. These are things like minerals, vitamins that some enzymes need to do their job so that they can fit the substrate. And most enzymes end in ase. So examples, hydrolases, oxidases are fancy names for enzymes. Okay. All right. Let me clear my drawings. And enzymes, they make reactions go faster. So this drawing as a student, I just think of a hill. If there's a hill, you need energy to get up and over the hill, right? So when an enzyme's present, there's not so much of a hill. It's not as steep. So you don't need as much energy to get from point A to point B. So if the enzyme's not present, there's a good amount of energy you need to get from point A to point B. That's going to take a while. But when the enzyme is present, you don't need as much energy to get from point A to point B. You'll go faster toward A than B, right? So we say enzymes lower the amount of energy to get from point A to point B. In other words, they lower the energy of activation. Fancy way to say they lower the energy needed to get from faster from point A to P. That's all. All right, clear my drawings, go to the next slide. So here, they kind of drew my little Pac-Man scenario, a little bit different. So what you got here in purple is the enzyme, and in this brownish coloration is what it binds to, the substrate, which in this case are amino acids. So the enzyme binds to the amino acids and brings them together so they form faster a peptide bond. And then the enzyme is done, it's done its job, it brought the amino acids together to form a peptide bond and it's unaffected, it's ready to do its job again. The only time you affect the job of an enzyme is if you increase temperature too high where it'll denature, or you decrease temperature where it's slower than it normally would be. Okay, what are nucleic acids? Okay, in your reading, and I normally ask students the same thing, and they like to say, oh, nucleic acids are the monomers to make them up are called nucleotides. Okay. Yes, they're nucleotides. But what's in a nucleotide? Can you tell me that? Well, in a nucleotide, you have to have a phosphate. You have to have a sugar. And then you have to have one of four nitrogen bases in the nucleotide. The nitrogen bases could be adenine, thymine, guanine, cytosine, or uracil. Okay? So, definition of nucleic acid for me has to have phosphate, a sugar, and a nitrogen base. So examples of nucleic acids in the body could be DNA. DNA are instructions to make proteins located in the cell's nucleus. And also RNA, which stands for ribonucleic acid, is an example of a nucleic acid. Okay, but the only difference is RNA is single-stranded and has ribose sugar instead of deoxyribose. Anyway, we'll get to the differences in the slides as they come up. So DNA, what's the purpose? Their instructions to make proteins. Which nitrogen bases do I find in DNA? Well, the nitrogen bases are adenine and guanine, cytosine, and thymine. Now, let me try to remember. I believe the purines are larger ring structures than the pyrimidines. Okay. Now, anytime you see DNA, it's going to be in a helical format. Helical, think of like a ribbon, kind of twirls, and it's double stranded. If I unwind it, it'll look like a ladder. Okay. So here you're going to have a phosphate attached to the sugar, deoxyribose, and then you're going to have one of four nitrogen bases, adenine, thymine, guanine, and cytosine. So this I put adenine. That's one nucleotide. Let's go to another nucleotide. Here's a phosphate, again, the sugar, deoxyribose, and let's say the nitrogen base here is thymine. Now, in one strand of the ladder, there's adenine. It'll always bind to, on the other strand, thymine. So A to T will always match up. And let's just say there's guanine. Guanine will always match up with cytosine. So that's what they're saying here. A to T, G to C. So you're looking at DNA. It's double-stranded in helical format, which means it twirls like a ribbon. Notice the nitrogen bases. Adenine pairs up with thymine. If it's got dashed lines, little dots, those are hydrogen bonds. Guanine will always pair up with cytosine. Take one nucleotide. Let's say it's adenine nucleotide. You'll see a phosphate. You'll see the sugar. So here's the we take one nucleotide. There's a phosphate. There's the sugar deoxyribose. And then this nitrogen base happens to be adenine. The other nucleotide here, you have the nitrogen base thymine. You have the sugar deoxyribose. It's just upside down. And then again, another phosphate here. Okay. So again, DNA is double-stranded. It's in helical format, which twists, and there are instructions for making protein. So we'll get to that later in the next chapter. Adenine always pairs with thymine. Guanine always pairs with cytosine. Now, let me try to remember. I said purines were larger in structure. I may have said incorrectly. Purines is, let's see, one ring, whereas pyrimidines may be two. Or maybe I have it backwards. Let me erase all this and look at the previous slide. Okay, so let's see here. Purines are adenine and guanine. So I go over here. Adenine is the double ring. So purines are double ring. Pyrimidines are single ring. Am I going to ask that? No. Okay, I need you to know what DNA is, though. I need you to know the nitrogen bases are going to be adenine, thymine, guanine, and cytosine. Okay, RNA is kind of similar to DNA. It's just the sugar is no longer deoxyribose, it's ribose. It is not double-stranded. Typically, it's single-stranded. And the nitrogen bases you find in RNA are going to be adenine, uracil. You'll never see thymine in RNA. You'll see uracil in its place. And then you'll see guanine and cytosine as well. And we'll get in more into RNA when we get to the next chapter, because there's different types of RNA. There could be messenger RNA, where I mentioned it's single-stranded. They could be what's called transfer RNA and ribosomal RNA. Now, ATP is also considered a nucleic acid. Well, why? Well, let's try to remember, what are the components that make up a nucleic acid? You have to have phosphate in its structure, which ATP has 3 for triphosphate. You have to have a sugar, and the sugar is going to be ribose in ATP. And then you have to have a nitrogen base, and the A in ATP stands for adenine. So you got the nitrogen base adenine. So yes, ATP is actually an example of a nucleic acid. Again, I'm working with a mouse. Okay, clear my drawings. So this is ATP. There's the adenine, the nitrogen base up top left. And blue is the sugar ribose, and you have 3 phosphates. Remember, similar charges should repel. Look at the charges. They're all similar. They're negative. And if you force them together, and you hook them up, when that bond's broken, that's going to provide energy to do work. That phosphate's going to kick off and it's moving. So it's going to be in kinetic energy. And when you give up one phosphate, you'll be left with two. That's called diphosphate. I never typically seen where there's just one, but if there was only one attached, then that would be adenosine monophosphate. All right, why do we need ATP to do work? How does ATP do work? By giving up a phosphate, okay? So what are some things that are going to be used to do work? Let's say you're looking at a cell membrane where the major structure, as you can see here, are bilayer phospholipids. You've got a protein embedded within the membrane. And when ATP gives up a phosphate, this channel, it's a protein channel, it's closed. But once it gives up the phosphate, the ATP, now the channel's open. You're allowed to do work. Here, ATP, you give up phosphate, can also allow muscles to contract, or ATP can give up a phosphate to help exchange or bring reactants together in a reaction. So that's the molecule all cells need to make in order to survive. And you need to provide a cell to make ATP. You need to provide it oxygen and a nutrient. All right, guys. That was one long chapter. Typically, I do these in two installments, but since I had to record it, I did it in one. But anyway, hopefully it recorded well. If you need to, pause it, rewind it for this chapter, okay? Anyway, I'll see y'all hopefully Tuesday. I'll pop in lab and let's get some of the concerns out with the lockdown browser. Okay, I'm going to end this and I will see y'all or talk to you next time.